Okay. All right. Hello, everybody. Welcome back to day three of WaterSoftHack Hacked and, day two of our actual tutorial. So, as Vidya said earlier, we hope you guys are finding it this whole tutorial useful, right? And, I hope you are learning something new that's useful for your work down the line. And we thank you a lot for participating and for your engagement. We're very happy with the questions that we got yesterday. Please keep them coming our way. And as you already know, Mihail and I, we are not water scientists. We are not hydro scientists. We don't have a lot of experience in this area. So if you want to share something, right, from your experience, and so that's relevant to the whole thing, things that we're discussing today, please feel free to share them, right? And if our hydro science examples are not up to exactly what you would like to see, if there's a better example, also feel free to share them and so on, right? So, would really appreciate if you interact with through Q&As, and we'll handle them as we go. Okay. All right. So, yesterday we talked about cloud computing, right? And today we are going to basically, go over the edge computing, right? So, cloud computing is essentially we're renting a slice of a supercomputer in the cloud, right? And today we are basically doing the opposite, right? So, we're trying to there's a small sensor that's standing in the river, right? So, we are basically trying to understand when to how to compute there, when to compute there, what are the constraints, right? What should you assume about the environment, and so on, right? So some expectations, it's 2 hours lecture like yesterday, followed by 1 hour tutorial, which Mihail is going to lead, right? That's going to be more hands-on. And but even though this entire afternoon is into is uh, for edge computing, we do not expect any background on electronics, right? So it's just about learning introduction level learning about the edge computing framework. So you guys may have some experience with data logger, right? Or field sensor and so on. So if you have some experience there, you already have some experience with edge computing, right? So as we're going to see later. Okay. So, right. So this is a recap of yesterday. Yesterday, basically, we learned how to rent a slice of a supercomputer and the entire framework of computing that's done there, right? So essentially, there was a big data that was too big to be handled, too big to be moved to a local computer, and we rented a supercomputer so that we can move our computing towards where the data is, right? And some frameworks that defines cloud computing is this paradigm of computing as a utility, where we rent computing, right, as a service, and we rent it by the hour, and whenever it's not needed we give it back to the provider, and we only pay for what we use, right? We thought about some frameworks, infrastructure as a service, right? So what are your expectations as a user for that paradigm? Similarly for platform as a service and software as a service. If you remember, if you go the infrastructure as a service route, you are basically like renting a black box machine, right? And you have to set up everything and build your software. Platform as a service is a software as a service on the other end is you as a user have no obligations as a you do not have to maintain anything, you do not have to code anything, right? And there is a end product sitting for you at the cloud. And platform as a service is somewhere in the between, where there is an API and you can still develop your application over the cloud, but you do not have the full control that infrastructure as a service provides. And so as we talked yesterday, right? So elasticity, right? So this idea of scaling up and scaling down compute resources as needed is what basically makes cloud computing so attractive, right? So especially for applications where compute demand is bursty, right? So for maybe for only once a month you might have to do your application, it's a lot of computing. Otherwise it's the demand is pretty little, right? If that's the case, then elasticity is the way to go. And one critical reminder is you pay for what you leave running on the cloud, right? Not what you end up using. So please be careful to shelve your resources when you are done, right? This helps protect the credits. This help minimizes the bill to the absolute minimum. Okay. So, but this whole cloud framework, right? And the applications that we're trying to develop had a one hidden assumption, right? Every reading travels to the cloud, right? So the application that we made yesterday, where we loaded data from Iowa River and tried to do next hour forecasting on the cloud, right? So what's the assumption there? So we get these readings from the river, right? So that's the data is captured by an actual device that's sitting on the river, right? We move it uh, we move it to the uh, um, uh, cloud, right? And like computation is done there, right? So today, basically, the entire question is like, okay, what to do when that's not possible. All right, okay. There is a question from Rahul that says, please explain elasticity in local
I'm
computers.
saying it.
Oh, okay, you are typing it. All right, thank you, Mehal.
Yeah.
Okay, so basically, right, and we're going to ask, right, what to do when that's not feasible, right, when that's not possible. Okay, so this is the roadmap for the next 2 hours, right? So first, we'll try to understand the motivation behind cloud computing, right? Why cloud-only model can break in the field, right? So there are some issues with the latency, there are some issues with the bandwidth, there are some issues with the power, right? Networks, right? So you can imagine if there's a big storm or a big flood, networks might fail, right? So the if there is a wired communication, right, between the sensor and the local local small computer, that could fail, right? So there are some constraints when cloud only. So if the computing part is only done on the cloud, it may not be possible, right? And we'll talk about what edge computing actually is, right? What is the core idea? The core idea is we are moving the computation towards the source of the data, right? Yesterday's idea was we are moving the computation to where the bulk of the data, right? The collected data, the large chunk of data sits. But today's idea is we are going to move the computing to where the source of the data is, right? And so we'll also think about the compute continuum, right? We'll go from this the edge to an intermediate device to a cloud, right? And we'll see what is the right level of computation for each for different applications. And we'll also think about what runs where, what kind of computation is typically done along the continuum. We'll also talk about the hardware that makes edge computings, the hardware of the edge computers in a sense, right? So the most critical thing is a sensor. There's a sensor that senses some physical aspect of the real world, right? So in our applications, it could be the level of the water, it could be temperature of the water, it could be pH of the water, and so on, right? And then the brain, right? So there has to be something that does some computation, but this brain is a limited brain in a sense that it's not as powerful as the cloud computing. It's not even as powerful as our cell phone device, right? So it's a very, very small computer. And then the radios that enable the hardware to talk to other local machines, right? Basically, the sensor has to be able to send the data somewhere, right? And it's done typically through radio communication. And the power source, right? So the batteries, right? And then the solar power that charges the battery. And then we'll talk about doing how to do more computation with less, right? So we'll kind of by the time we'll go to number four, we'll understand the entire paradigm, right? And we'll think about how to do do we need to send all the data that's out there, right? Or do we need to process something, right? And so on. And then we'll think about some paradigms that make doing more powerful computation with small compute resources, right? So these four things are basically what I will cover, right? And five and six are what's going to happen uh, uh, the in the afternoon session led by Mihail. Right? So we'll try to build some small ACE application, right? And for water science, where we'll simulate real sensor networks, right? And then try to see the smart girls that we'll build. And we'll do some hands-on, I mean, I'm going to talk about it, right? But Mihail is going to lead this, number five. And number six, we'll do some preview, right? I'll actually show what we're going to do, and then talk about what's going to come tomorrow. All right, okay. So it's day two of a 3-day story. Yesterday we talked about cloud, right? There is a big machine, it has a lot of data. You're renting a small slice of that computing to do what's meaningful, right? And that compute that you rent could be small, could be scaled down, up as you need, right? So that was the story yesterday. Today, we push the intelligence out to the sensors in the field, right? So basically, yesterday there was a big hub that's the intelligence center, right? Where all the computing is done. Today, we're pushing the intelligence towards exactly the place where the data originates, in a sense, right? And tomorrow we'll basically combine them, right? So that, we can build more powerful systems. So our application is going to be same thread as yesterday. So we'll try to build a flood early warning system. Today will design the smart girls that stands in the river and thinks for itself, right? And but you cannot do like large scale machine learning training there. So it has to be a lot more simplistic than yesterday, right? So the question that we're basically asking today is how much intelligence can we really pack into a small, cheap solar-powered box, right? And why do we want to do that, right? Because in our current infrastructure system, clouds already exist, right? So why do you still want to pack some computing towards a small, cheap devices? Okay, so let's think about this story, right? So, and let's try to motivate this. Imagine a gauze in a cannon, right, at 2 a.m., right? And so that's trying to uh, that's trying to measure the water level, right? So basically a sensor that matters most in a flash flood, right? So it's a stays gauze on a mountain creek, and basically an hour's drive up from a dirt road, right? It has a small solar panel, a battery, and uh, the cell signal is not that good, right? The storm basically makes it important. That the storm that makes it important, right? So basically, why are we placing the sensor is to basically go measure when storms happen, right? When the downstream river is going to rise, right? But the storm that we're trying to measure makes basically cuts it off, right? So the cloud, basically, the cloud computing that has a lot of this super intelligence, right, may not be reachable for this small sensor when it really matters, right? And as you all know, right, so flash floods are very dangerous, right? So basically, a small creek can go from ankle deep to flooding cars in 30 minutes, right? And the gauges are there to basically warn us about this possibility, right? And then heavy rain basically it makes radio links unusable, right? And the clouds are not reachable, right? So basically um, a small computing, right? 1 second of computing could be a lot more useful than a lot of very superpower computing that sits in the cloud, right? So okay, so the yesterday when we discussed about cloud, right? So we didn't talk about its limitation, right? So but there are some constraints that make uh, the cloud computing a bit uh, uh, like you know uh, basically not a possibility in certain instances, right? So the first thing is bandwidth is scarce, right? So the LoRa, the radio communication that these sensors usually use, right? So they cannot send a lot of data, right? It moves like kilobits per second, right? You cannot stream the raw data like every millisecond of a data by a radio, right? The next thing is power, right? So there is usually on these water gauzes there are no plug-in systems, right? Wall outlets. So there is a solar panel and there is a small battery that must survive cloudy weeks, that must survive the summer months where the trees grow and then blocks the sunlight, right? And so on. And as we'll see later, it has to communicate through radio by sending out radio signals, right, to nearby devices, and that is the biggest consumer of the power, right? So the entire this whole setup is kind of against it because the device has to communicate through the radio signals, and the sending out radio transmissions are very expensive. And like there is a cost of low latency, right? So as we said earlier, flash floods are they are measured in minutes, right? So it goes like this very, very quickly, right? So we cannot wait for round trip computation, right? So say collect the data in the sensor, radio transmit to the nearby devices. That device sends the the data signal to the cloud where the computation is done and then back, right? So that is not possible. So round trip basically like transmission of data through this congested network may be too slow for a lot of applications that we care about. And the last uh, constraint is that the network fails exactly when we need it, right? So there's a high likelihood of network failing exactly when we need it, right? So the weather is bad, radio transmissions are weak, right? So the storm is there, the radio transmissions fail. Sensors might get the communication links might be disrupted, right? So basically this design, right? So the our sensor network system that we have must keep working independently even when the transmission lines are turned off, right? So we have to think about all these constraints to build a robust sensor networks. Okay, at this point, are there any questions? Okay, I don't see any. I see all the questions that have been answered. Okay, so please, keep sending questions our way. Okay. All right. So, these are the concrete outcomes for today. So basically, the first three things are conceptual that, we'll cover mostly in the lecture. And the last two are going to be uh, done in our uh, hands-on session this afternoon. Uh, right? So we should be able to explain edge computing and when it beats cloud-only design, right? So we should be able to name the parts of the sensor, right? What is the brain of the sensor? Sorry, of an edge device. What is the sensor part, right? What is the radio? How is it powered? So we should be able to choose hardware and communication links for a field deployment, right? We should be able to design um, on-device detection under the bandwidth and power budgets, right? So we should be able to do that. And we are going to run an edge simulator and measure what the smart design says, right? So basically, right, this is what we're going to do. So, just to clarify things, right? So we are not going to we do not require electronics background, right? So there is no you don't have to program a real physical device. So these are basically hardware ideas, but hands-on is purely on Python in the same Jupyter Hub that we did yesterday. Okay. All right. Okay. So, why is cloud not enough, right? So, as we talked about earlier, the field is far, far away, where the sensor is actually done is far, far away from the cloud computing, and the communication links are fragile, right? So, these are these basically constraint is why this cloud-only system, right? Imagine flash flood warning system that only does computing on the cloud, right? So that is not enough. Okay, again, I'll pause for questions if there are any questions, right? So I hope we understand a little bit about what's going to happen today, right? And uh, what our expectations are and what we're going to do this afternoon. Okay, all right, let's move on. Why the cloud is not enough, right? So yesterday's architecture that we built, if we look at it honestly, right? So there is a one pattern. The sensor is basically a thing that senses some physical aspect of the real world, but is a dumb messenger that doesn't do anything intelligent, right? It senses things and then it reads, right? And then it sends. That's all it does, right? And all the thinking, right? All the intelligence is basically done at the cloud level, right? So this is basically the architecture of the sensor system that we designed yesterday. So the sensor that stays in the river senses, right? Measures water level, pH, blah blah blah. right? It reads the stage every few minutes. It just transmits to a local device, right? And then that somehow the data is like, sent to the cloud. The cloud stores the data, right? Has all the models, right? Like, the model that we designed yesterday was lived in the cloud, right? And it decides basically predicts what's the water level going to be an hour down the line, right? And if that prediction is very, very bad, then we send the alert, right? So every step depends on the link, right? So the connection between devices. If we cut the wire anywhere, the gauze basically, cannot do anything, right? It just senses, and then that number is on its own, not that useful, right? So basically now what we're doing is this third box here has the intelligence, right? We are moving this intelligence down the line on the sensor device, right? So that's all we're doing. But we also should appreciate the fact that this third box, the machine that lives in the third box, is super powerful, right? And the machine that lives in the first life, the first box, is very trivial, right? It's a very cheap $30 machine, right? Doesn't have a lot of transistors, right? And can do, its ability is limited in a sense. Okay, all right. So let's look at the constraints of the cloud in more detail, right? So how far is the cloud really, right? If we think about the computation that gets done in the gauze itself, right? It's immediate, right? So what the data is sensed, we do the computation, it's immediate. The gateway on the next hill, right? So imagine there are lots of sensors, all spread out along the river. There has to be something that aggregates the data, right? That reads all the radio signals, and but is connected, is slightly more powerful than these individual sensors, and sends the data to the cloud through some communication channel, right? So this is the gateway. So if you do some computation there, it's milliseconds, right? It's usually available, right? Because it's in the vicinity. And if you send to the cloud on a fiber, right, from the this gateway device, then tens of milliseconds, right? So it's kind of if there is a cloud computing, or if there is a powerful machine in some power station, right, or a river power station, then you can imagine this level of distance between the edge device and the cloud device, right? To the cloud on a rural cellular, that's really, really far, right? So is it always available? Well, it's available when it works, right? But it may not be the cloud, right? But during the storm, right, it may not be reachable, right? So so the communication link is cut, right? So the biggest takeaway is that the latency statistics assume, right, there is a permanent link between the edge device and the cloud device. And during a severe thunderstorm, this assumption, is the risk, right? Quietly is the most susceptible failure link, right? So whenever we need the decision, right, that must be timely and guaranteed, we should move the computation as close to the sensor as possible. Okay, so the next constraint is the bandwidth, right? So the field, connections do not cannot carry gigabits of data, right? So it's usually done on kilobyte per second, right? So the most communication is done through LoRa, which is a radio communication protocol, or satellite link, right? And these are not these are channels that cannot move a lot of they have very limited bandwidth, right? So streaming raw data through pipes is not possible, right? And then it's a lot of the costly, right? If you use satellite communications, that's going to be very, very costly, right? And but the pressure sensor can produce a lot of data, right? It can sample at the rate of 100 hertz, right? So there's a mismatch, right? Sensors can produce a lot of data, right? A million times faster, thousands times faster than what the connections can carry, right? So something has to decide what is useful to send, right? So there has to be some intelligence in the local vicinity of where the data is collected that says, look, this particular number is worth sending, or like these numbers aggregated at this resolution is sending, right? So there is a choice that we have to make. Either we throw away the information blindly by sampling, by reducing the sampling rate, right? So instead of so you cannot send everything that you have sent, so send every like the thousandth number, right? So that is risky because you may miss the most important numbers, right? Or we put some intelligence at the sensors to decide what matters, and then we send that, right? So this bandwidth constraint already forces our hand, right? So basically this we have to put some decision maker on the sensor device, and that itself is edge computing in a sense, right? So that itself forces our moves us towards edge computing. The next constraint is power, right? So the field station the the sensor that we have usually lives on a solar panel and a battery, right? So I'm sure those of you who have some experience working on the field, right, have seen these boxes, right? So these are very robust boxes, right? And they have a lot of dry cell batteries which are rechargeable and have some solar source. So now, like this is the surprising part, right? So it's basically the transmission, right? That the sensor has, the device has to make, that is ultra power hungry, and not the computation itself, right? So on this chart, we have on the y-axis we have the current draw in milliampere, right? So when the device is in deep sleep, right? So basically, there is no current flowing, right? So it's on the current is almost 0 milliampere, right? Approximately. If the device is reading, right? So it's sampling something, right? The cost is pretty low. If we do some computation on the edge device, right, that's also pretty low, right? So we move from 5 to 40. But when we transmit the data, right, so the milliampere rises to 220, right? So you can see, right? So this radio transmission that the device has to do, right? So that's the sole purpose it's there, is already the power bottleneck, right? So computation, right, that we have to do by comparison is a lot cheaper, right, in terms of power, right? So the energy budget is dominated entirely by how often we transmit, right? So it's cheaper to think, right, than to talk in a sense, right? So than to transmit blindly. And so it kind of justifies, right? So everything that we do today, because the devices are there in the river and their core job is to send the data out, right? And if you add computation on top of it, the most crucial bottleneck, right, which is the power, is not affected that much, right? So every message you avoid sending buys hours of sleep, and buys probably minutes of computing as well, right? So it's better to for the sensor devices to do some compute, gather some meaningful things, and then reduce the amount of data that they send out. Okay. So the next thing that we want to next constraint that we want to talk about is the reliability, right? So the storms always attack the network first, right? So at times engineers design for average network availability, right? But the sensor networks for hazards must work in the tail, right? So must work in the conditions when there is an hazard, right? So in 2008 Iowa flood, right? There was a big flood in Iowa. So and every major hurricane, like a hurricane, that has happened in the US states, communication infrastructures have failed, right? So at the height of the event. So this is hence that's a problem, right? So the communication bandwidth between the devices fail. So the sensors network doesn't end, that doesn't work, and the early warning system that we have designed may not work, right? So that's why disasters still happen, right? That's why the flood event, the terrible flood events in Texas last year and this year, right? So where flash floods killed multiple people, they still happen, right? Despite our river systems having all of these sensors. So why does it happen? Because at times towers lose power, right? So the regional storms black out cell sites, right? The backup generators do not last for days, right? The power grids are affected, right? So the powers may not, the towers that communicate, right, that facilitate radio signals, they may lose, or especially cell signals, right? So they may lose powers. Networks get congested, even especially during hazards, right? Everybody's calling on 911, right? People are in need of emergency, right? So people's lives are exactly at risk. So it makes sense that the networks have a lot of demand. So the links themselves degrade in bad weather, right? If the communication is not wired, right? So if it's wired, the wire has higher chances of failing, right? So either ways, there is a high possibility that the links will degrade. Right, and then these the failures correlate with extreme events, right? The flood, the outage, and the data gap all arrive together, not independently, right? So we still have to build something that works when when all of these things conspire against us, right? In some sense. Okay, right? So the idea for today, as we said earlier, right, is to move the computation to where the data is born, right? So yesterday we brought the code to the cloud, right, where the data lives, because the data sets were too big to move. Today it's the same principle, right? But the motivation is different, right? It's not because the data is too heavy to move. It's because the communication links are too fragile, right? So the question is, so basically, the question is, how do we move the computing towards the source of the data in a principled manner? So this is a question I asked this before though. Will we get to know the project so that we can do ourselves? I have just the first week access. So you mean will you get the Python files that we developed? Yeah, I think so, right? I think we'll upload this to WaterSoftHack website and you should be able to access there. Right, and then the fellows will do hands-on project on top of what we have developed next week, or they might want to do something from scratch. It's up to them. But for other attendees who are just attending, you will have access to everything that we have done, right? You will have access to the slides, you'll have access to the videos, you'll have access to the Python scripts that we worked yesterday, we're going to work today, and we're going to build tomorrow. Okay, all right, let's move on. Okay, what is computing, right? So the simple answer is processing where the data is born, right? So let's define it. Edge computing is processing data at or near its source, right? On the device that produced it, or a machine that's next immediate to it, right? Instead of shipping every raw byte to a distant data center, right? So for water computing, right, so this is basically a river gauge, right? uh, the edge is basically the boundary of the network, right? The last hardware before the physical world, right? So if you think of this flood system, we may have the data center that collects everything, right? We have the communication links, we have and then we have small local hubs, and then we have those local hubs talk to the field sensors, right? After field sensors, it's the actual real world, right? The river or the field, right? Or the creek, whatever, right? So it's basically this first device, right, that interacts with the real physical world. That's the edge, right? And the computing that's done there is an edge computing, right? To make this, to put it very, very simply, right? So what does it buy us? It's faster because we are computing on the data set that's being collected right there at the point of data collection. It's cheaper, right? Because as we saw earlier, radio transmission is the most expensive part of in the power budget of the edge device. And if we send insights and not the raw data, or even if we send the raw data that's most meaningfully sampled, then it's cheaper, right? Both the bandwidth and the batteries are safe, sturdier, right? So if we move the computing toward the edge, it works even when the network communication fails, right? So like, it has a lot of advantages. Right. So now, like, the edge computing thing is like, used a bit loosely nowadays in industry, right? So like, even like, smart thermostat to like, regional micro data center gets called the edge, right? So like, but the edge essentially is something that, the best way to think about is something that like, interacts with the physical world, right? So it's at the boundary of the your like, digital system that you have built and the physical world. Okay. So this is the like, compute continuum in a sense, right? So let's think of like, again the like, flood system, flood warning system that we're thinking about, right? So if we think of like, where exactly does the computation happen, right? It goes from the riverbank to the data center, right? So the edge device is the microcontroller inside the gauze itself, right? So which is like sitting in the river. And then there may be a box, right? So that gets on the bridge, right? Or like, nearby hill, right? Which is like, wall powered, which is like, a little bit more robust. And like, it basically communicates with all nearby sensors, right? So you can call it a gateway or a local edge device. And then like, this like, the data collected here, right, can move to the cloud, right? So the cloud is a cloud. It's like, centralized system, right? So that has like, that aggregates all the devices, like, all the data, and has a lot of compute resources, right? Examples are like, Jetstream 2 application that we built yesterday, right? AWS systems that are out there, right? So here basically, like we have infinite compute and storage powers, right? So like, what are the different like, characteristics of these devices, right? So the edge device is like, is immediately next to the data, right? It's like, right there, but it doesn't have a lot of memory, right? It doesn't have a lot of powers, right? So it has to work on milliwatts, and it has to work, it's like, it can only store like kilobytes of memory, right? It can run things like threshold checks, right? Filtering, right? And like, basically threshold check is also like, how we do event detection, right? In a sense, right? Spikes, detect sharp rises, and so on. On the other hand, right? So these gateways, right? So they are basically, few, some one communication hub away, right? In a sense. Uh, right? So this is like, milliseconds away, right? And it's wall powered. So there is a question that says from Mayuran that says, does digital twin systems utilize edge computing? Okay, so that's a great question, right? So the digital twin paradigm is basically, like you build like, mathematical or like, computational model of the entire physical system, right, in a computer. So there is a like, real world system, right? You can imagine there is a river flowing, right? There is like, like there's a creek that flows into the river, that flows into the basin, that goes into the ocean, and so on. And the digital twin basically builds a computational model that mimics that, right? So it's like, twin of the physical system that lives inside a computer, right? It could be a mathematical or like, or like, machine learning, whatever model, right? So in a sense, right, I mean, how do you like, make the digital twin like, an honest representation of the real world is, utilizing the data that's collected by the edge devices at the end of the day, right? But it doesn't have to like, depend totally like, on edge computing, right? It can be independent. Let's say I have collect like, thousands of data, right, from like, for 2 3 years, and I move that data to a cloud, right? I can just build my digital computing on the on the cloud. I mean, it might be more robust, right, and more accurate up to like, up to day to day if I connect with the edge devices and keep updating it, right? But it doesn't have to, right? So I would say it's an independent system. But thanks for the question. Okay. All right. Okay. So what kind of devices are here, right? So the this uh, the The computing inside the water gauze is probably a microcontroller, right? Very, very small, right? So has some like, fixed programming done, right? Is not too flexible. On the gateway, I think there is like, a small computer, probably a Raspberry Pi, right? With a box, heavy box, fortified box, right? And like, wall power, right? And like, is more reliable, right? Is tolerant because it's talking to multiple devices, right? So in the cloud, we all know, right? As we talked yesterday, right? So, like, in a sense, the computing capability goes from left to right, right? And then the immediacy and resilience goes from right to left, right? Uh, so, like, designing the right system, right? So, where we exactly place computation, while knowing how much computation and how much resilience we have at each level can help us build the best possible, alert systems that are out there. Okay, there is one more question. Does the edge device transmit data to the gateway? Yes, usually yes. Right? So, I mean, we can design things whatever way we want, but the most, common framework is that the edge device runs on a battery, right? And talks to a nearby gateway device through, wireless communication. It could be radio transmission or through, yeah, cell phone, right? Using, cell phone towers, right? And the gateway computing might, there could be a series of gateways, right, before the data is actually collected on the cloud, right? But at some point this gateway is going to be connected to, will have a robust communication infrastructure. Looks like the USGS gauze station box installed on rivers also utilize hybrid edge cloud model. Probably, yeah. So this I'm not familiar with, but I would expect so, right? So as you will see today, right? So we'll see some advantage of edge computing, right? And we'll see tomorrow that why, this integrating this entire framework is the best possible thing to do, right? So I think a system like USGS should use this entire edge cloud model. Right? Thank you. Thank you for the question. All right. Let's move on. Okay. So, there are some trade-offs between clouds and edge, right? So the distance to the data as at edge device is 0. For cloud, it's far, as we have, established. Compute and memory. Edge device, goes from kilobytes to megabytes. It's very small, right? For cloud, we can assume it's unlimited, right? When you are comparing, especially when we are competing with the edge. Power, right? Again, right? Milliwatts, right? It runs on a small battery and solar for the edge device, but it has is powered by an industrial grid for a cloud computing. Right? So the latency to react, it's microseconds on edge, right? So this is where there is an advantage for an edge device. Whereas milliseconds to never, right? Never when there is a communication link failure. But usually up to a minute is not a, a minute is not a bad estimate, right? So there is a real latency. Works offline, edge devices, yes. Cloud, no, right? The whole uh, cloud framework assumes that there is accessibility, right? And you can connect to it from everywhere. So it's edge device is best for fast local computing, always on decisions that you have to make, right? Cloud is good for heavy models, right? So NWS, what those models that we talked about yesterday, right? It gives the global view, right? And where you have to store historical data. Okay, so now the question is, okay, what should run on the cloud, GauZ, right? And what should run on the cloud, right? So it's best to put it on the edge device if the decision cannot wait for a round trip, right? If the link is weak, right, costly or fails in the storm, right? So these immediate things that for which you need reactions, you want to do it in the edge, right? And the raw data is huge, but the insight is small, right? Let's say you are getting a flat line of river level stays flat, right? Doesn't change. There's no point in sending out the same number over and over again to the cloud, right? So you might want to do some computation that kind of detects the river is stable, right? Which is like, very cheap in terms of computational cost. And you can just do that in the device, right? Rather than sending that to the cloud and then the cloud figures out that, okay, there is no risk. And you want to do computation that must be done when everything else is down on the edge device, right? Or like, devices that are like, one hops away, right? But you also want to make sure in your system that there are like, resiliencies, right? You have multiple gauzes nearby, right? You have like, a lot of different sensors talking to a local hubs and so on. So we want to do the computation on the cloud if the model is too big, right? So let's say you are doing like, a big forecasting or like nowcasting system that relies on very, very big machine learning systems and ingests a lot of different type of datas, not just like, simple numbers that are collected in the river gauge, right? If that's the case, you have to do it in the cloud because nowhere else, the resources, compute resources are not available anywhere else, right? So you need the data from many sensors at once. As I said earlier, you are training, right, or exploring, right? So you're like, doing like retrospective analysis of like, when dangers could happen, right? Or you are trying to understand how rivers behave. You want to do those things on the cloud, right? Okay. All right. So there is a like, so like, we have to give our due to the hydrologists, right? So like, they were doing computation on edge devices before it was cool, right? So you may be working with like, Campbell data loggers, right? So they have been used since 1970s. So these are boxes that records the readings, right? And a human basically drives out to the places where the data loggers are kept, and they download the data manually, right? So this is a edge device, right? So which is like, which has been going on for a while. What's really, really new is like, what the computing capability of edge devices, right? $5 chip today can carry more compute power than like, workstation computer from 1990s, right? The radios are very, very cheap compared to 1970s, right? And machine learning, right? So especially like, this paradigm of tiny ML, right? So this is like, um, there is like, some hypothesis that can kind of say that, like machine learning can be done a lot more efficiently, right? And size of the models can be reduced by a lot, right? Especially like, and like, this whole, there is a paradigm of tiny ML, right? So where you build like smaller and smaller neural networks with the same capability of large machine learning models, right? So they can fit to some extent in like smaller devices, right? So this box and the data logger, right, is not just there to record anymore, right? So it can like, filter, it can accept, it can adapt, it can like, make some prediction, it can decide, right? So it's an upgrade from like, just from a computational viewpoint, right, on what was being already done, right, in hydroscience. And it's not like, concept that like computer scientists build and then is being like, moved to hydroscience, right? So like, this in a lot of like, domains where like, real world sensing was critical, right? So the it was not called as computing, but this framework, right, that like, trying to do something smart on the field has been there for a while. Okay, so let's build some vocabulary, right, for all week. So we'll have a sensor, or we'll call it a transducer. It's a physical, like, this is a thing that turns a physical signal, right? Something in the real world, right? Like a stage or like water pressure, water level, turbidity into a number in a computer, into a digital number, right? Which can be transmitted, which can be manipulated, which can be stored, right? So if that device does it, we call it a sensor. A microcomputer, a microcontroller is a tiny single program computer, right? It's not even a Raspberry Pi, right? It's like, a FPGA, right? Or a microcontroller, right? Very, very small single program computer, right? So it's the Gauge's brain. A gateway is a nearby box. You can think of it as a complete computer, but it is like a limited power, complete computer, right? It's a gateway. It talks to a nearby sensors and then bridges the sensors to the internet, right? So a telemetry or a uplink is the data that a station sends to the cloud, to the network, and downlink is the command that comes from the cloud, right? A duty cycle is basically a fraction of a time the device is awake, right? So it decides how long your battery is going to last. And MQTT is the protocol that these edge devices use to talk, right? So on the websites that we build talk on HTTPS protocol, right, or HTTP protocol before we added security. Systems like Zoom, I think probably it runs on UDP. I'm not sure, but Skype used to run on UDP, right? So and it's just a protocol, right? Another protocol, right? That MQTT that lets IoT devices talk to each other. So it's basically the devices have to agree on language, right? You have to say like, look, both of the devices that are communicating, right? So they have to say like, this is the language I'm using before they start talking to each other, right? These languages are essentially what we call protocols in a sense, right? So MQTT is the protocol that lets IoT devices sort of talk to each other. Okay, so at this point, I think I can take some questions. I can check for some questions. Uh, I don't see any that's not answered until this point, but I see there are like many that Mihail has answered. Thank you, Mihail, for taking these questions. Okay, so if there, okay, so there are two new questions. Can you please explain the round trip part? Why does the transmission from sensor have to be a round trip? Okay, so in a sense, so let's say the sensor is trying to determine, right, in a sense, right, or a person nearby the sensor is determining if there is a the flood or not, right? If the sensor itself does no computing, right, then the data has to travel to a place where the computation has to be done, right, and the final result of the computation has to go back to the sensor, no, right? So that's why it's a round trip, right? I hope that makes sense. But if the decision maker is already at a place where the cloud is, right, then I mean you don't have to send it back, right? But somebody has to tell somebody that there is a flood coming on, right? But I think the weather affects the gateway that uploads the data packet to the cloud as well, right? Yes, right. So that's the whole point that we're trying to make, right? So this communication links, right? Between the edge device and the gateway to the data center, they could all be affected by weather. I typically would think gateway to the cloud is a lot more resilient, right? Maybe there is a a fiber net that's buried under the ground, right? If that's the case, it's to some sense, to some level, it's less susceptible to failure, but it could also fail. Okay. Any other questions? Please feel free to send them our way. Okay. What is the local storage range for device edge and gateway local edge? So, I think the edge devices probably kilobytes, right? Or at best megabytes. I think the gateway, the first level that talks to a sensors, are probably still I would say megabytes, right? But multiple megabytes, 256, 512 megabytes, and so on. That, but I mean, these things are variable, right? Depending on what we place where. So you could build a system that places my Raspberry Pi inside a sensor, right? It would cost more, right? But it's not out of the realms of possibility. So can the sensor store data it cannot transmit until there is a connection? Yeah, I think that's the assumption. Yep. Yep, right. So the sensor doesn't have enough it senses a lot more than it can store, right? And so that's one point. The second point is if there is a risk, right? And then the computation has to be done, right? And there's no point in storing the data if the flood has already happened and you can use the data to predict flood, right? So So the cloud, may easily predict that, we all know at that point, right? The flood has already happened. Okay, these are all great questions. Thank you very much. Okay, there's one more question from Rahul. How can we make sure duty cycle adaptive waking up more frequently during rapid stage rise so the battery powered gauges don't miss the flash floods peak? Yeah, so I think, yeah, so like, right, so this is like, one example of how to make the sensors more intelligent,
And that's
right? So,
exactly what we're going
yeah.
to do in the workshop.
Yep, yep. So this is a great question, right? So you can see, right, now because we started talking about these things, these questions become more like pertinent, right? So if the water level is rising, how can I make sure that, my device is not sleeping as much, right? So, you can have some like, thresholding, right? You can have some small models that kind of like, wake up the device, if there is an imminent threat. Okay. All right. Thank you very much. Now maybe we can take a bio break for it's what time is it? Let me stop sharing for a bit. Okay, so it's 11 a.m. Central. I think it's 12 a.m. In the East Coast. So maybe we can take a 10 minutes break and come back at 12:10 Eastern, 11:10 Central. All right, thank you. I'll go ahead and pause recording. Okay, let me. So, but yeah, I think like if you want to build on top of it, right, on top of what we do today,
Yeah.
that's totally fine, right? And if you want to do something like, that goes beyond the example that we do today for like, but just uses edge computing, that's also fine. I think the projects, the fellows like, capstone do not have to like, it could be on cloud, it could be on edge, or it could be on hybrid, right? So that's totally fine. But we'll see, like, hybrid things are the best, right? And maybe that, like, sways your opinion a little bit. Okay, all right. So let's continue, right? So okay, now like we know what edge computing is, right? What are the advantages? Let's see like what actually does the edge computing, right? Let's look at the hardware. Okay, so there are like five things, critical things on a smart gauze, right? Or the higher science edge device. One is the sensor, right? So it could be like the radar based sensor, it could be ultrasonic sensor, right? Or it could be like pressure gauze, right? Or like so these are things that like measure something specific of the real world. There is a small computer, right? A microcontroller that like runs the detection logic in a sense, right? There is a communicator, right? So that it could be a cellular device, it could be a satellite device, right? It could be like a LoRa device, right? And so it basically transmits some signal to a nearby device. There is something that has to like power the device. So it's usually a battery, right? Or a solar panel, right? So usually there is also a charge controller, right? Or some combination of these three things. And there is a enclosure, right? So this device has to live in the field, right? It's not inside a house, it's not inside a a warehouse, right? It's like it has to be there out in the wild. So there is a weatherproof housing, right? There's a mounting, right? There's probably a lightning protection, right? And so on. It's probably tied, right? So it's fixed to a particular location if it sits in the river and so on, right? So the total, like, the everything, costs anywhere between like, a few tens of dollars to hundreds of dollars, right? The engineering is like, not in any part, right? So it's a combination of like, everything. Okay. Basically, like the parts are quite cheap, right? So compared to a cloud computing device, the edge device is very, very cheap, right? And that's the takeaway from this slide. Okay, so what does a brain of the edge device looks like, right? So it could be like a simple microcontroller like ESP32 or like Arduino, right? It takes from like anywhere between $5 to $20, right? Runs on like milliwatts. It can only do one program, right? Probably runs forever on its battery, right? And only has like kilobytes of RAM. right? Enough for like tiny rules, right? And very, very small models, logic, rule-based models, right? Nothing way too fancy. There could also be Raspberry Pi, right? So like, depending on different versions, right? Or like, if you like, so it costs from like, few tens of dollars to $100. But I'm like maybe like, a few $100 also, right? So it can run like, full scale Linux machine, real Python, right? But it cannot have like, these big, large scale machine learning models, right? It cannot host them. But I think there are like, small enough ML machine learning models, right? Especially like, tiny MLs that can fit in a Raspberry Pi, right? So it can implement, it's a lot more powerful. So I would think of a microcontroller as a like a smart gauze level, right? Or like, but Raspberry Pi as a gateway level. But it also depends, right? So I mean, like there are some systems where, I'm sure like, Raspberry Pi is like lives on the at the gauze level also, right? So like, there are also like something more powerful, right? So like, AGI board systems, right? So like NVIDIA Jetson or like Coral, right? So these are slightly more expensive than like, single board computers. So they have like, onboard GPU tensor processing unit, right? For like deep learning, vision, right? They have like, probably have some camera, right? To collect the data and also like, do some like, leverage some like, vision models, right? Or like, audio recording, and they can also like, process signal processing and so on. Okay, so like, what are the sensors, right? How does like, a gauze senses the river? So probably like, it's a combination of like, some of these devices, right? So a radar or like, ultrasonic stage probably looks down at the river from a bridge, right? Or like, or a nearby structure, there's no contact, right? And like, no fouling, right? So this is a modern favorite. A tipping bucket rain gauze, probably counts like just counts the rainfall pulses upstream, right? So this is like, probably the earliest warning input that we have. A camera, right? Also a sensor, right? So it takes images, right? Or like, or like, it's a, or you can also like, do the velocity, right? So like, by taking a video, right? And also like, looks for debris, right? Ice and so on. So this probably needs an AGI model, right? If you have to use camera and then a vision model. There's also like, pressure gauze. It sits in the water, right? And basically, like, as you all know, right? I think how deep the sensor is, kind of like, how much pressure the water senses, the gauze senses tells us it how like, deep it is, right? So that basically tells us how like, high the surface has risen, right? So like, it's very, very accurate, right? So you can imagine, right? So the pressure gauge exactly can determine the like, level of the water much better than like, like something that a camera can do, right? Unless like, the camera is like, very well calibrated. There are like, markings and so on. But it's exposed to like, debris, right? Something might hit the sensors. There are also these water quality sound, right? Which can capture, which can like, sense the temperature, turbidity, conductivity, oxygen levels, right? pH probably, and so on, right? We also have this uh, the soil moisture level, right? And a probe, like it can like, compute or like sense how saturated the water shed is, and like, whether the soil is like absorbing the rain or like, is losing water and so on. Okay, so how does the gauze like, communicates, right? So there are like, different mediums, right? The LoRa and cellular are the probably the most common mediums, right? So LoRa is a like, a radio low range radio communication channel, right? So it's like, it requires low power compared to other channels, right? And it can only, but has a very limited bandwidth, right? It's best for dense local networks, right? Like this, like we'll see some examples, right? So this Iowa, like, river system gauze that we have, right? So like here, like, LoRa is fine, I think. So the cellular is like, like basically like, it's like, it uses our cell phone towers to communicate, right? So gauzes has a SIM card or like, or like, or like eSIM, right? And it uses LTE to talk to other devices, right? So range is wherever the towers can reach, right? Power is like it has like slightly more power, needs a little bit power, more power than LoRa, right? And the data it can still like send a modest level of data, right? So which is like pretty good. So like it's best for the workhorse where the coverage exists, right? So it's like if your sensor is in a place, it's not too remote, right? And there is a reliable cell phone tower nearby, you might as well like do cellular communication, right? The satellite range is anywhere on the earth, right? Power is like slightly more than the cellular, right? Data, it's like tiny smaller data because it's the communicating with satellite is quite expensive, right? So where would you put it? If there are like canyons, right, where like the canyons, right, where like this is like the range of LoRa is not enough and there are no cellular towers nearby, right? So you might want to use satellite. So like but if you're living in like city, right, or a campus, right, or like nearby the labs, then you might also use Wi-Fi, right, to send the device to communicate. Okay, so how does the edge devices lose their power? I have no idea why it keeps moving. Okay, so sleeping is very, very cheap, right? Like, the device is barely active, it's not doing anything. Sampling, right? So if it's sampling every few minutes, then the typical like the typical rate is like 5 milliampere for a few seconds, right? So this is also like very, very cheap, right? Thinking about each sample, about 40 milliamperes, right? Still like pretty like compared to the how much battery, right? 10,000 milliamperes that's available. This is also pretty cheap, right? But transmitting every seconds, right? So that's expensive, right? So that's like the most costliest thing that edge device can do, right? So like we can uh, pack as much computing as it's possible given the processing power of the edge device without thinking too much about the power, right? So which is good news, right? So at least there is one thing that we don't have to worry about. So, like, let's look at one example, right, of a like, edge, devices network. So this is the Iowa Flood Center's bridge sensors. So I think, like, you guys might have used IFIS data, right? So this is like, the net data collected by the sensors in this network. So there was a big flood here in Iowa, right? I think Iowa City also, like, the areas near the cities were drowned, right? And then the like because of this, the Iowa Flood Center at the University of Iowa was born, right? And it builds its own sensor network instead of waiting for like full service gauges, right? Like the USG gauges data that we used yesterday, right? So it's basically a cheaper, a larger, like you can think of it as a like a more complete, high resolution network of cheaper devices, right? So there are like both advantages and disadvantages, but it gives you higher coverage, right? Essentially, so it's a like collection of simple ultrasonic stage sensors bolted to highway bridges and solar powered devices, right? And like connecting like basically over the cellular network, right? So it's like, a dense network of cheap, frugal, good enough sensors, right? And basically this is telling us like, the sparse network at times, right, which have more powerful devices are not good enough. And like, we cannot build this dense network of expensive devices, right? Because I mean, it might be like, enough, we might have enough budget to buy it once, but it has to be maintained, right? It has to be replaced, right? Things go, and like, for more expensive devices, you need like, more like manpower, right? So more skilled manpower and so on. So it's expensive to buy, it's expensive to maintain and so on, right? But like sometimes like good enough, more denser network of good enough sensors are good, are like are useful, right? So this is what this case study is telling us. Similarly, right, flood NYC, it's ultrasonic sensors, right, over the streets, not the rivers, right? So like again, right, different from what we have seen so far, right? So it's basically its goal is to catch the flash flood warning from the drainage, right? So it's powered by solar and talks in LoRa, right? Cheap enough to like cover like do the blanket surveillance of neighborhoods, right, over NYC. And so this data is also open, and it kind of determines the city's response, right? So whenever the city has to pay attention, they can, right? So why does this changes everything? Because a federal gauze, right, like USGS, right, costs tens of thousands to install, right, and 15K a year to run, right? But a smart sensor is is a few $100s of parts, right? So it's it's not the same thing but cheaper, right? It's like a different thing, right? I mean, if you buy cheaper things, you are getting less powerful things, right? But oftentimes, it gives you early warning system, right? Especially if it's added on top of the system that already has the gold standard gauges, right? So this gives us a high resolution, right? So the full stream gauges, they are like surveyed, maintained, right? They are like well maintained, right? They have been providing decades long consistent records, right? And they have been the backbone for models and floodplain maps, right? But they are sparse because you can't really do it everywhere, right? But this cheaper things, right, they are stays only roughly calibrated, but they are everywhere, right? So and they can help complement the gold standard gauges that we have, right? So on the other hand, they are dense enough to feel small creeks, right? And they are cheap enough to lose one and we don't have to worry too much, right? So they because they do not incur a heavy financial burden. Okay. All right. So what kind of softwares can we do on the edge devices? Right. So the main story is don't send everything, right? Send the story or send the alert, not the entire stream of data that you sense, right? So you can send events, transmit when something happens, right? A threshold is crossed or something trend is broken, right? The water level rised before the I don't know, rainy season, something, right? Something unique happened, right? Detect that and send that. The other idea is send the summaries, right? Maybe one message with the mean max, right? Replaces a 60 raw readings, and maybe you can do especially when the water is flat, right? You can maybe that's enough, right? Or you can just send the delta. So stay silent when nothing changes, right? Speak only when the value moves, right? Have some a check for the changes in the data, right? And this is good because as we discussed earlier, right? The power is communication is what drains the battery of the edge device, right? So we they this small computation can happen at no extra cost, right? So it's always worth doing it. Or we can compress, right? So pack, right, whatever we can into a few bytes as much as possible, instead of sending one number and a lot of strings of zeros, right? So the takeaway is so the river, if you can imagine, river is boring most of the time, right? Nothing really happens, right? At that time we don't need to send these raw readings every few minutes, right? Or every few seconds, right? We can compress the data, right? And send when necessary, right? So the next technique is have some logic on the edge device, right? So the flood onset has a signature, right? So maybe the stays crosses the flood stays, right? The stays here could be I don't know, the flow of the river, the water level, whatever, right? So just check if this stays is over some predefined flood stays. If it is, then send the alert, right? Or monitor the rate of rise, right? So take the differences, right, over two consecutive reading, or readings that are a few minutes apart, and then check if that difference is greater than some predefined threshold, right? Send an alert, right? So I think for flash flood, right, the rate matters more than the level probably, right? The rapid rise rules fires while the river is still below the flood level, right? And it can be thought of as an early signal. So just but like this more than me. So okay. So, you can also do like an adaptive sampling, right? So when the river is flat, like, you don't send anything, or you don't even like, do like extensive sampling, right? But if there is a change, right, then like, your like logic activates, right? And then like, you sample more, right? Do a little bit more computing and then uh, send the signal. Okay, and we can also do tiny ML, right? So these are like machine learning models in like kilobytes, right? So we train the model, right? Train the full scale model in the cloud, and then we shrink the model, right? Basically like prune the model, right? So there's a hypothesis called like what is it called? Lottery ticket hypothesis. It basically says that like once you choose the initial random weights, there are certain parameters that are more significantly important than everything else, right? And everything else can be pruned without losing way too much information, right? And like we see that as like basically like a lot of the parameters of the neural networks being zeros, right? Which do not like impact the predictions too much, so they can be pruned, right? And you like after the model is small enough, you then deploy to the edge, right? So and then it runs on the GUS on like small scale machine that's already there. So what kind of things we can do? We can do anomaly detection, right? So if there is a sudden rise of the number, if the number is a sudden drop of the number, right? If like if something breaks the trend, we can use ML to detect it, right? We can define smarter triggers than thresholding, right? Maybe the machine learning model incorporates something like a lot more logically complicated than like simple threshold, right? So which is like learn from the flood onset patterns in the past. We can have like vision camera gauze, right? Again, like there's a camera that can like take like continuous pictures, and we can have a small vision model on the right, but which adheres to this tiny ML principle, right? So we can use like TensorFlow Lite or like as impulse, right? Which like trains big models and then shrink and deploy. Okay, so three ways we can fit like large models onto in a matchbox level computing that's present in the edge device, right? So quantization is like basically like a uh, like aggregating information in like small quantity, like small quantas essentially, right? So instead of like storing a 32-bit integer floats, we'll store 8-bit integers, right? And maybe this can still help us to approximate computation, right? But it's like significantly smaller and far cheaper, right? And the accuracy, like hopefully it's like you lose something, right? Because like you are using like far less powerful computing, but like it's still like approximately good enough, right? If there is a flood, does it really matter that level is either 40.5 or 40.6? It doesn't right? So like maybe like just the fact that the flood is there, it can be done just using the 8-bit integers, right? We don't need like all the entire power of like precisions of the floating point numbers. We can also prune, as we talked in the tiny ML slides, right? Most trained weights are like near zero and do not do anything, right? So we can just delete them, right? And keep the skeleton that like matters the most. We can also do knowledge distillation, right? You have a big model that's trained on the cloud, right? And then we train a smaller like smaller student model that tries to mimic the big model, right? We think of the big model as a teacher, and then we try to think of the smaller model as a student, right? So the end, like we distill the knowledge that the teacher has, right? And then we transfer the knowledge from the teacher to the student, right? And we can stack all these three, and then like we can basically like move a model that's crowd sized to a gauge sized, right? While keeping the most of the skill of the ML that we care about, right? So these like large machine learning models that live in the cloud, they are like nowadays like these foundational models, they're like general purpose, right? Maybe we don't need general purpose model, right? Maybe we need some small models that does like specific things for us, and those like can be like are done at a much smaller scale. Okay, so we should think of like outages as like a routine weather and not disasters, right? In a sense, to make things more reliable. right, for the uh, cloud computing, sorry, for the edge devices. A well-designed gauze will treat a dead link as, like, as expected, right? So it will survive, right, and it will not lose things, right, and it will find ways to, like, critically alert, right, do some computing and then find a way to alert, right? So how do you do that? Log locally, right? So like maybe have a SD card, right, and then log it, right? Buffer the backlog, right? So if there is a link down, then don't throw away the messages. You try to store it. Now everything may not be possible, so like keep as much as is necessary. And if there is some logic that can be implemented on the edge device, then you can keep the important messages, right? Backfill and reconnect, right? So check for, like, reconnections, right, and ship the queue. So if there is, like, critical thing, then have a fallback path, right? So if, like, critical alarms try the backup, right? Maybe you send an SMS burst, right? So if there is a flood, right, and your, like, radio network doesn't work, maybe there is a SMS that works, right, or like SOS that works, right, or a satellite ping, right, or a local siren, right? Maybe there's a siren device nearby, right? So always try, like, having a secondary means of communication, especially for, like, critical alarms are important, right? So that, like, makes communicating, like, implementing logic on edge devices even more important if these things are already in place. Okay, so like we should know when is not the right answer, right? Like I think we had a similar cloud is slide for cloud computing yesterday where we said, like, when the cloud is the wrong answer, right? So there is usually a hard ceiling on compute resources, right, for the edge device, right? So few like kilobytes to megabytes of RAMs, right? Limited power sources, right? So the big computational things cannot simply be done, right? So there is a fleet management pain, right? So you can imagine, right? So one edge device is not enough, right? You will have, like, a large network of devices spread across, right? So like managing and updating on, like, all 250 of these devices, right, while, like, physically traveling or, like, communicating over a poor link is not as straightforward as basically restarting a, like, virtual machine on the cloud, right? So there is some cost associated with edge computing, right? So the devices are at, like, mercy of the physical world, right? There could be lightning could destroy it, floods could take sweep it away, right? People could break it, right? Or, like, wild animals can, like, come and kick the device, right, and throw it off its, like, fixed position, right? So the field is going to, like, eat some of the hardware away, right? So that's basically, like, the cost of deploying things in the real world, right? So it's not as protected as a machine that lives in a warehouse, air conditioned warehouse, right, nowadays. Okay. And there is also, like, this is, like, the biggest critical, like, shortcoming of the cloud computing. There's no global view, right? A gauze notes its own number, and any computation that's done on the gauze is only on its number. It doesn't know what's happening at a gauze that's 5 kilometers away, right? So it cannot see the upstream number, it cannot see the basins, right? Only a cloud computing, right, which pools and aggregates all of these numbers can see, right? So at times, right, just doing, like, A's is not the right answer, right? So you may want to, like, obviously, if you, like, take the knowledge of the swarm of the knowledge produced by, like, entire 250 boxes as in the previous example, the model is going to be a lot better than, like, working on a single number, right? So, like, uh, um, if there is a way, right, to, like, merge the cloud computing with edge computing, it could be more powerful. Okay, so what are some good practices, right? So we should assume that edge devices are physically accessible, right? Anyone, right? Anyone, like even the person you do not want to access the device, right, can physically access it, right? Because the device lives on a remote stage, and, like, your team, right, may not physically be there, right? Or, like, it's very hard to, like, physically protect the device, right? So we have to assume anyone can walk up to it, right? So there shouldn't be like, plain text, right? If you don't want anybody to like, know about it, right? So it's good practice to encrypt it, right? And like, encrypt the SD devices, right? Encrypt the knowledge, encrypt the like, transmissions, right? And that are being done. So you also want to sign the updates, right? So over the air firmware must be cryptographically signed, right? Or someone else's code runs on the gauzes, right? So you have to have like, basically like, protect the computing that's being done on the gauze, right? So you don't want somebody's like, random code to run on the machine, right? You want to also encrypt the uplink, right? Sensor data, and alerts have to be encrypted. Otherwise, somebody might can do like, man in the middle uh, attack, right? Even the LoRa, right? So like, even when the edge device is talking to an intermediate uh, 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 gateway device, right? Even that should be encrypted, right? Otherwise, someone might mimic, the edge data, sending a signal to the LoRa gateway device, right? And produce like, false numbers. Right. So it's also best practice to make the device fail safe in a sense, right? So a compromised or confused gauze should say that in the data, that hey, look, I don't know, right? Rather than say sending out zeros or like staying silent, right? So that kind of informs like whoever is aggregating or like looking at the number, right? They're saying that something's wrong here. Maybe this data is not as trustworthy, right? So it makes the eventual model better. Okay, so right, so what are we like, so what kind of edge devices or like edge computing can we do for water science, right? And uh, uh, what are like our expectations for this afternoon? So we are going to simulate this hardware, right? ESP32 class microcontroller, right? Which is going to be the brain, and it's looking down like basically it's like a down looking radar stage sensor, right? So it's like not physically in the river, but it's like sensing it using a radar, and it will use a LoRa radio, right? And like and has a cellular fullback, and has some memory, right? And has some like some level of power. So this is exactly what we're going to implement, right? So as a simulator, I mean, we're not going to like code the hardware, but we are going to simulate this hardware in Python knob for knob, right? So we're like we this is not a like in a sense like you are like, if you think about it, then you are actually programming this. You can think of it like the programming this device and like the programming that we're going to do today are going to be exactly the same, right? So we are trying to like implement this behavior in today's exercise. We'll try to sample every 15 minutes at a base flow, and every 1 minute when the level is rising, right? And we'll run the level plus rate of rise rules on every sample, right? So like check for every sample, check if the level is above certain threshold and the rate of rise is above a certain threshold, and we'll like mimic the device to send hourly summaries, right? And we'll buffer everything through outages, right? And sleep at microamps, right, in every spare second. So this is what we're going to implement in Python today. Okay, so right, so this is like the whole picture in one table, right? So every number will be hopefully be reproducible in today's notebook, right? So we'll simulate a storm, right? And then try to produce these numbers, right? So the naive streamer will send 1440 messages, but a smart girl will get like same level of alert system with only 25 messages, right? So this is like it takes the radio data from 84 kilobyte to 1.5 kilobyte, right? So and the nice thing is like it list like it basically extends the battery life from 2 months to like a few number of years, right? And like in the during the network outages, right, will the flood be detected in the naive streamer? No, right, because it doesn't have a fallback communication, right? But the because we said there is a like we said there is a communication that has a cellular fallback, right? It communicates through LoRa radio, but there is a cellular fallback in like our simulated device, right? So it's going to like be still be able to alarm the local neighborhood, right, and send a SOS signal. Okay, so this is not what we are going to implement today, right? But if the sensor is camera, right, there is a it has a lot of power, right? It can see stages, it can see debris and ice, which the pressure gauzes cannot, right? And the ultimate, but it's the ultimate bandwidth nightmare, right? So AGI is what makes the cameras deployable in the field, right? So it's the tiny ML framework helps, really helps here, right? So we read the water line against the staff curves, right? No contact, right? So it's lives above the surface. We can compute the velocity from the video, right? So if we take sequence of pictures, right, we can compute the velocity of the water. We can look for debris and ice, right? We can send the verdicts, right? And we don't have to basically send the entire video, right? The edge device will take the video, right, and do some computation there, and then it can basically send the summary, right? There is a debris, right? There is a water level rising fast and so on. Okay, so there are so this could be some ideas for the fellows for their capstone project, right? You don't have to basically build the flood warning system, right? You can think of precise irrigation, right? Where the edge devices monitor soil moistures, right? And decide whether the water needs to be added, right? And you can uh, save water, right? Basically, right? If the enough moisture is already in the soil, then maybe you don't need to water the crop, right? Or if the soil is too dry, then you might want to alert the the farm, saying that look, these crops are at risk of drying up, right? You might want to water. Quality early warning, right? A sound basically detects a containment spike, right, at the intake, and the closes the gate, right? So like a control system in a sense, right? You can also design like a real-time control, stormwater gates, right? Pumps tune themselves to the storm as it happens, right? So basically edge device monitors, right? And it makes a decision to pump the water, right? Or close the gates, right? Whatever it is locally, right? Without sending the data to the cloud, right? And coastal and buoy networks, right? So we can monitor wave, we can monitor source sensors, right? And on satellites and summarize things as necessary, right? So when edge computing is the wrong answer, part two, right? This is when power and networks are fine, right? So this is when things are better, don't do edge, right? Do something better, right? The model will not fit, right? Again, right? So if your computational need is big, right, then you cannot force it on edge computing, right? Do it on slightly more powerful machines. The logic changes weekly, right? Because if that's the case, right, then you don't want to deploy it on the cloud, because you need some place where redeploying is very easy, right? And it's not a place where you have to drive all afternoon, right, just to fix a code in one particular location, right? And it takes you a month to visit all the sites, right? So that's not possible. And even when the fleet is tiny, two sensors in the lab, right? A cable is cheaper than a distributed system, right? You don't need to, I mean, no need to think of this is a network system, right? You can just do local computing. Okay, so what are we going to so basically what are the summaries, right? So these are the few mental models of edge computing to keep, right? So the field gives us milliwatts, right, level power with kilobits level storing, right, and a very small bar of signal for communication, right? So our computing has to design for it, right? So this is the playing field, right? And we cannot expect for more, right? This is what is given to us, and our computational solution has to be designed for it. But there is something that comes to our advantage, and it is that it's easier to compute than to transmit, right? So, like it's like cheaper to compute than to transmit. So we might as well implement computational logic, right? And transmit the final result or the insight, right? So edge basically means to bring the code to where the data is born, right? So this is the the boundary between the real world, which produces the data, and the digital world that first senses the data, right? So and we exactly do computation there, right? So that's the edge, and cloud is basically where the aggregated data in large models live, right? So we might want to have these differences in our head. So like one frugal way for to make the gauze live for years is to slip deep, right, and sample adaptively, and then send events, right? So and these whole things should be orchestrated by a logic, right? Computing basically dictates how the device slips, how a sampling is done, right? And for the device to slip long, right? You have to do adaptive sampling, right? Because if the threat levels rises, right? If the event that you're trying to detect, the likelihood of that event rises, then you want to sample more, right? And when the likelihood is low, you might want to make a device deep sleep. And finally, autonomy is the point, right? So the warning system must fire, right? The messages must be sent even when the network is down, right? So having a fallback communication channel, right? Or at least SOS services available to the device is quite important. Okay, so this afternoon, what are we going to do? Right, we are going to basically replay a real storm. We'll use a live USGS data through a simulated gauze, and we'll create a synthetic storm. If that doesn't work, right, we'll have a synthetic storm as a backup. We'll meter the knife streamer, right? So we'll first see what does a knife streamer does, right? And then we'll program a smart brain, right? So now we're adding edge computing to this knife streamer, and we'll see what are the distances, well, sorry, what are the differences, right? And we'll then cut the network mid flood, right? And we'll say that the knife streamer is not able to do anything, but if our the thing that we program still detects a flood, it should be able to fire, right? Because it has one more channel available to it. Okay, but right, so one critical limitation of this entire framework is that it's blind to what's going on everywhere else, right? So it can only sense the number that's immediate to it, right? So things could be faulty, right? Because there is no overall picture, right? And tomorrow we'll kind of we'll see that um, uh, if we combine the cloud and the edge, right? We'll have a much better hybrid system, and this is usually how the real world systems, right? Real world systems are built. That's it. That's all Mihail and I have prepared for the lecture. I hope you get sense of what edge computing is. How is it different from cloud computing, right? What are the characteristics of edge computing? Why is it important, right? And what makes up a edge device, right? What are its limitations, right? And why is it advantageous to do computing in edge from time to time, right? I hope those things are I hope I've been able to convey those things. And we'll do some hands-on exercise this afternoon, right? Where you will see adding some logic to a naive meter can make things a lot more interesting, right? Can be quite useful. Okay, at this point we're happy to take a few questions. Okay, let me open the Q&A panel. Okay, Mihail, thank you for answering the other questions that we have seen so far. Okay, so there is a question. Thank you for the presentation. That's very informative and will be useful along the way. The USGS probably has the most experience in the world in deploying and maintaining sensors in all conditions, especially the transmission part. What is their framework for storage and transmission? That I have no idea. I think I'm probably sure it's like, because those are like, more powerful devices, they probably use cellular, right? So that's my guess. Okay. Again, I'm not an expert in hydroscience, so this is just my guess. So like, having read about their system a little bit, right, which is quite comprehensive, but is not quite dense, right? So it's probably not in like very very remote places. So I think it's probably cellular or like satellite, right? Could also be satellite. Yeah. Thank you for the presentation. Could these sensors be used to detect flash floods events in streets? Yeah, yeah, that's the whole point, right? So, like basically, like, you detect them, you do some local computing, detect them quickly, and then, send out SOS, right? Instead of like, waiting for like, the entire communication with the cloud.
Tomorrow, actually, we're going to try to detect it before it reaches the city, basically. So we can take action a few hours before.
Okay,
So we'll try this.
sounds good, Mihail. Okay, any other questions? Okay, if not, you still have like, opportunity to see Mihail and me this afternoon, right? Where we'll do hands-on, we'll do some simulated storm, right? And like, try to build a smart edge device. We'll use the same framework as yesterday, right? The same notebook, right? And same link. And we will start at 1 p.m. Central, which is 2 p.m. Eastern, right? So see you guys then. So, Nishal, the link is the same, right? So we'll have the same link. We'll have it open, right? You can disconnect and connect back again. All right. Thanks, Nishal. Okay. All right. See you guys in the bit. In a bit. There's a question that says, "Did you create a Slack page?" No, I don't think so. But I think there's a Discord channel. I'm not there, but I think like all the fellows are there. Vidya is there. And I think Mihail and Krishna, right? Our two grad students are also there. All right, I'll go ahead and pause record.
All right, welcome back, everyone. So today we'll do edge computing. Now, if you haven't bookmarked your Jupyter Notebook link, I'll put it in the chat. You can just paste this IP address into the browser. You can let me know in the Q&A if there's any issues. Since there are no issues, then we can get started. So again, you should have a copy of the repository I shared yesterday. So you should be able to just go to day 2 and you should have the code over there. Okay. So today, Dr. Bijaya presented to you basically edge computing. So now we're going to start designing sensors. We're going to have a simulation of a sensor because we cannot really access a real sensor right now. But we will also have data from USGS sensors, which are actual sensors. So you can count on it as a real edge device. Okay. All right. So, first of all, let's start with part 0. So now, we will have a river, all right, but we will try to design a storm, okay? So how are we going to do this? Okay, let's take a look at the formula. So first of all, we're going to have a base flow, And then we're gonna try to basically create like a spike. We can do this using interpolation, and I'll show it through the code how to do it. Okay. Again, from yesterday, you remember NumPy and pandas. NumPy is for arrays, pandas is for uh, tables, and matplotlib is for plotting. If you have any questions, just say in the Q&A. Okay, so let's go into the design storm function. Again, we're going to do 14 days, and the storm is going to start on day 10, basically. And as I said yesterday, it's customary usually when you work with NumPy to use the seed 42. Okay. So now, again, n is the number of, actually this time, n is the number of minutes. Yesterday we did hourly, now we're going to do minute granularity. Okay? And what we're going to do is we're going to basically try to create a spike. And how we're going to do this, we're going to use the interpolation, the interp function from NumPy, which takes in what? It takes in first the variable we're gonna uh, it like the variable we're gonna interpolate over. Okay. Then it's gonna take the points we're sampling and the values we're sampling at those points. Basically, we're gonna see how that looks on the graph. Okay. And one thing to remember that np.interp is piecewise linear interpolation. If you're not familiar with this term, it basically means we have points and between them we draw lines. No curves, no splines or something like that. Okay. So this interpolation happens here. Okay. Now, again, we're going to create a random number generator and we're going to add to this spike, we're going to add the daily wiggle, which is basically like a base flow wiggle that happens daily, and some noise. All right. And similar to yesterday, we're going to create indexes, but this time the frequency is 1 minute, not 1 hour. And we're going to return the Panda series. A Panda series, it just means that it's a table with just one index and one co value column. It's a way of storing function data points, basically. All right, let's plot it and let's see how it looks like. Okay. So, as you can see, for the first 10 days, we just have some noise and the river wiggle basically. That happens every day. And then on the 10th day, we can see there's a spike that bypasses the flood gate basically. So during that day, there's going to be a flood. Okay, and we basically are going to try, what are we going to try to do is first design a sensor that is naive. It just sends to the cloud data every minute, basically. So we call this time-based sampling. And then we're going to have a smart sensor, which is going to only send when the threshold goes beyond the floodgate, which we're going to call event sampling. All right. Yeah. Any questions so far? I can go deeper into the code if you want. Okay. All right. So now let's see. Let's try to fetch again live data from USGS from the USGS API, and we're basically gonna do the same thing we did yesterday. So let's see how that looks like. All right. So remember yesterday, we were down here basically, and now it seems the river has spiked. That's interesting, but again, it's not past the flood threshold because it's not the rainy season here right now. when I wrote this code, it was basically saying C mostly boring. That's why it usually sleeps, but it seems the actual example is not that boring, actually. Right. Okay. Now let's go into the actual details. So in Dr. Bijaya's presentation, we had I think it was the E32 microcontroller, right? So these are the specs for this microcontroller. Basically, when it's in deep sleep, it only takes zero point 0.0 on milliamperes, and that runs all the time, basically. So usually, batteries, I mean, you guys are most probably familiar. You've probably taken physics classes or maybe some engineering classes as well. I'm not sure. You can let me know in the Q&A. But like battery charges are usually uh, the units we tend to use are milliampere hours. You know that milliampere hours is basically going to be a unit of charge. So we can see basically if it draws 0.01 milliamperes in deep sleep per day, we're going to have 0.25 milliampere hours, which is nothing. Okay. Now, for reading, we're going to be drawing 5 milliampere hours, and the sampling happens every 50 milliseconds. And as you can see, this also takes almost nothing, despite the sampling frequency. So brain thinking basically means the microcontroller is doing some calculations, maybe taking some averages or doing some form of interpolation, whichever kind of processing you want to do. But as we can see, this also doesn't take almost any energy basically. But then comes the radio transmission. So because this one actually engages an antenna and it requires specific circuitry, it tends to draw much more power, despite the fact that the sampling frequency is the sending frequency in this case is around 2 seconds. So in our example, we're gonna have one battery which is gonna have 10,000 milliampere hours. To make a comparison, I think my phone has around 5,000 milliampere hours, so this battery is twice as big as the one in my phone, basically. But we'll see, despite that, depending on the microcontroller and depending on the edge device settings, it can actually drain extremely fast, right? So one radio message tends to be around 60 bytes, right? But the thing is, the radio costs roughly 1,000 sensor readings per message. So it's not feasible to send a radio message very often. This is why here even we have a very big difference. We read every 50 milliseconds, but we send every 2 seconds, basically. Okay. Now, we are going to be using object-oriented programming. I'm not sure if any of you are familiar with this. It's a programming paradigm. If any of you are familiar, please let me know in the Q&A section. But if not, either way, I'm going to explain how it tends to work. Okay. All right. So let's dig into the code. Okay. So HW is basically a plain dictionary of realistic field hardware specs. Um, this underscore here is just a readability separator. It basically means 10,000 milliampere hours. Sleep MA is basically how much uh, current basically we take while we're sleeping. Sensor MA, same thing, but when we're sensing. Sensor second is the sampling frequency. MCU MA is the uh, thinking charge, not charge, current. And MCUS is basically the how many times per second are we thinking or calculating, basically. Same with radio MA and radio S. Okay. Now, this construct here is basically defines a tiny one-line function. In computer science, it's called the lambda function. That's why we even have the lambda keyword. So what it does basically, it converts so basically draw milliampere for seconds into milliampere hours, basically. So we're going to have the milliampere hour converted directly from milliampere and second. It's a simple mathematical formula. Okay, yeah. So now the radio costs around 700 times more than the sensing. So that is why we're gonna see the smart gauge is gonna win. Okay. So first, in object-oriented programming, we tend instead of having just lines of code, basically declarative lines of code that tell you what to do. In object-oriented programming, we tend to have classes, and these classes have functions which define the behavior. Okay, so the class itself will store attributes or an attribute is basically like, for example, let's say I have a dog, right? So I can have a dog class. Basically, its color is an attribute, right? And I can have functions or methods, they're sometimes called, which define the behavior of a class, basically. When we instantiate a class, we say it's called an object. So a class is like a general class, like let's say the human class, right? But an object in this sense will be an actual human, like an actual instantiation of this class. Okay? So the class gauge basically is going to define the blueprint for the gauge object. And this function here, it's used in Python. It's the standard a function for creating a class. We call it in object-oriented programming a constructor, basically, right? So once it runs, you create a gauge, you set up its starting state, and self here refers to the actual object that we are creating. Okay. Now, okay, so we're gonna store the river records on the object. Basically, we're gonna store the stage, the net up, the buffer on failure, how much energy we used, the messages that we sent, the amount of bytes that we sent. Basically, a buffer. A buffer just basically stores all the messages that are to be sent. We're going to have a cloud log, which basically is going to log everything we're doing, and we're going to have some alarms, basically. Yeah. So this is basically kind of like the gauges ledger. So basically, again, we have energy used, message bytes sent, a buffer for failed sends, a log of what reaches the cloud, a list of local alarms, and the current minute index. So again, we can see that the gauge is starting to display some form of intelligence. Okay. Now, the thing is, these ones are going to start empty and they're going to fill up as the simulation runs, right? So every counter here becomes a number that's going to appear on the final scoreboard. Okay. Now, we've defined the properties or the attributes that this gauge is going to have, right? Now we need to define what it can do, basically. So we're going to do this by defining functions inside this class. So the first function is read sensor. So let's call it ability one, right? So it has the ability to read sensor costs and sensor energy, and it uses a little bit of MCU energy, which is added to the ledger, basically. So again, you can see self.used MAH basically means we're updating the property used MAH for the object we're going to be creating. Okay, and we're just going to add the sensor MA and the processing MA. Okay, any questions so far? I've gone a little bit fast, so if there's any question, just stop me and let me know.
Yeah, I don't see any questions so far, Mihail.
Yeah, if there are no questions, we can go to the next function, next ability. So we're going to call it ability two, which is transmit. Okay, so sending always burns radio energy. That's the main problem, even if it fails, you see. So the radio is still going to physically try to send the message, right? So if the network is up and the cloud receives it, we're gonna log and count it, basically. Okay, if it's down, like a smart gauge, for example, we have a buffer on failure property, saves it, and is going to try to resend it later. But a naive gauge that's not that smart is going to remove it from the buffer and just going to lose it, basically. So this one method is basically the heart of the whole outage lesson, basically. Okay, so this is ability two. Now, ability three. So flushing the buffer, basically what it means, we try to do a backfill, which is while there are buffered messages and the link is back up, we try to resend all of them in one burst. Okay, one per burst, basically. So you're gonna see here self buffer.pop is going to remove the oldest one, basically, and each filled record is going to log both its arrival time, okay, and its original measure time. So when it fired and when it got sent, basically. And it's going to be tagged instead of data, we're going to tag it backfill, basically. So this is how the smart gauge is going to tell to the cloud that it healed itself after an outage, basically, if the connection was lost. Okay. This is technically not ability three. So we have ability one is reading the sensor. Ability two is transmitting. Flush is basically like a helper function, more like it, basically. And now we're going to have ability three, which is going to be basically firing a local alarm. So if it detects, basically, it's going to fire the on-site siren. Basically, it's going to sound around the facility or wherever it's placed, and it's going to record the time and the reason. Now, crucially, and this is very important, this doesn't require a network, basically. And this is the whole point of the edge's autonomy, basically. For this one, it's just like signaling an event. Okay. Now, the next part is for us to simulate it here, basically, we need a simulation loop. We need to actually have this gauge running and simulate that it's running, basically. So how this is usually done, we have a run function, and what it does for every minute, basically, we set the clock and we call the step function, basically. Okay? And the one method, each brain must define. So a step method is very important because it basically tells you what it basically updates the state of the gauge. Okay, so after the loop, we basically add the always on deep sleep drain because even if we're not doing anything, the gauge still takes battery power. And the run usually returns self, so you can chain it with dot report later. This is not that important, but either way, let's go into the report function. So the report function, okay, what it does basically. Now the thing is, think of this object as doing its own job, right? But the problem is we need a human to be able to interface with it in a sense, basically. We need to be able to read. So what this function does, it basically turns the ledger into human numbers, basically. Okay. So we have some battery life math, which basically gets the battery storage or capacity and divides it by how much we used per day. And so it creates basically an estimate of how many live days we've got left. Okay, then it prints years if that exceeds 360 days. Otherwise, it prints months or days, basically. Okay. So now, this was a very fast introduction to object-oriented programming, and of course, this doesn't do justice to this amazing programming paradigm. But for our purposes here, I think it's pretty self-explanatory. But the key object-oriented programming idea is that the gauge never decides when to read or send. Basically, it's programmed to have a specific behavior, and it only provides the abilities and the bookkeeping for our purposes, right? The decisions that actually happen, they happen in the step function, okay? and which is the function that any brain, let's call it, needs to supply. Okay? Now, this separation is why the same engine can fairly compare a dumb and a smart strategy or design, basically. Okay. Any questions? I'll pause for a little while and ask. You can ask your questions. It seems there are no questions. Everyone's familiar with object-oriented programming.
So this is a Gauss simulator, right?
Yes,
Okay. And the run function basically is activated. So this is what kind of like, does sensing in the loop.
yes,
So you are going to create an object instance later.
yeah.
Instances.
This is, yeah, for those of you who are not familiar with OOP, this is just the class definition, basically. When we want to use it, we're going to instantiate it, we say, which is basically going to run this constructor here, and it's going to create an object, which has all of these properties and all of these abilities or behaviors, basically. Okay, if there are no questions, let's run it. And we can say the engine is ready, the battery is loaded, and this is how much one message costs, basically.
So
All right, let's
does
go
the
to
simulator also like, is there a solar that charges? No.
yeah, yeah. Yeah.
Okay.
No, it's basically a battery, but we can have it solar charged as well if you want. Oh, someone's
Not
got a
right now,
question.
right? Okay.
Yeah, no. Is OOP preferred for code organization or it matters in performance? Very good questions. The thing is, usually most of the software that's written on these microcontrollers is very simple, right? But for a simulator like ours, or like for more complex softwares, OOP is usually preferred. Yes, it's not just code organization, but it's also the ability to use it. Basically, it's much better to have a class with a defined behavior then string 1,000 functions and combine them later. But it also depends on the paradigm. There are functional languages which can outperform uh, uh, OOP designs. Like I think Haskell is a functional language. It's all real time. Show it like the engine is ready. Yes. So when it runs the loop, it will run in real time, basically. It's going to be running with us right now. Any other questions?
Okay. So at this point, you're just like mimicking the hardware, right? So this is
Yes.
like a simulator. Now, based on this, you're going to like, design a naive and a more smart, uh, like,
Yes.
sensor.
Okay. Seems there are no more questions, so let's go to part two. Oh, can you explain flush buffer again? Yes. So what the flush buffer actually does is it basically, let's say there was an outage, right? And the gauge could not send any data to the cloud. Basically, what happens is we have something called a backfill, right? So a backfill usually in data processing, like for example, let's say you have a time series, right? And you have three data points, right? And let's say you need more of this, or some of the data was stored or collected somewhere else. A backfill basically means you're going to take your time series and augment or basically add more data points from the back. That's why it's called a backfill, basically. And how this is done, it's basically done through this buffer.pop 0, which is basically going to take, we have like it's kind of like a stack here, actually. We have a stack and we're going to get the oldest one and send it. Does that make sense? And when we send it, we're going to send both the time it was sent and and also the time it was measured. So we know actually that the time it was sent is not the time it was measured because that could mess up the time series. All right. So now, yeah, sure. Uh, Now let's start with a naive streamer. So this is going to be our design A. And again, this code is very simple, but I need to explain what this actually means. So when we define a class and we do this, basically we will put in parentheses the name of another class. This is an OOP pattern called inheritance, basically. It means this naive streamer class is a gauge, basically. And because of that, it inherits all of the properties and the behaviors or methods of the base class, it's called. Okay? So the naive streamer class basically inherits gauge and only adds the step function because when I defined gauge, I didn't write the actual step function because the step function will basically depend on the actual properties of the gauge. Okay, right. So basically, these three lines are the brain of the first gauge. That's it. So what it does, basically, it just streams. It basically reads every minute and it sends it. That's it. That's the whole brain. This is called naive streamer is a function. No, naive streamer is a class. So a function is always defined in Python with def. A class is defined with the keyword class, basically. So naive streamer is a class that inherits from the gauge class. Right. Okay. Yeah. So this is called time sampling. So it samples every time, like every time, no matter what happens, basically. Okay. Now, so basically, what are we doing here? We are instantiating an object. So whenever we call this basically when we call the name of the class and we put parentheses, this basically calls the constructor of the class. And because the constructor of the naive streamer class is basically the constructor of its base class, which is gauge. So it's basically going to call this init function. Okay? And this basically what it does, it creates it and then runs the gauge. Okay? Now it runs and we want to see a report. Remember what the report does? It basically shows us a human readable version. Okay? And in Jupyter Notebook, I think you guys are familiar. If you just put the name of a variable or function or whatever, it's gonna show it as output of the cell. So let's run this. Nice. So here it shows, okay, what's the design name? So the design name is Naive Streamer, okay? It shows us how many messages it's going to send per day. So it's going to send around 1,440 messages per day, which is very wasteful, okay? It's going to waste around 84 kilobytes per day. I mean, this doesn't sound much, but it can accumulate if you have thousands or hundreds of thousands of even millions of gauges, basically. And as we can see, the battery life will just last us for 2 months. So, of course, it's a hassle. I don't think that anyone is going to be paid to change the batteries like every 2 months for millions of gauges. So, we need to do better. Okay. Any questions so far? Any questions on inheritance, on instantiation, on any of the mathematical details or anything? Okay. So now let's go to part three. Oh, where is the line that tells the sensor to read every minute? Yes, it's this line basically. It's naive. So we instantiate the class basically, and we take this. This is an object basically. When you put this is called sometimes the dot operator. So basically, when you put an object dot run, it's gonna basically run. It's gonna run the run method or run function of the object. So this is the line that does it.
But maybe you want to go back to the class definition and show why it runs every minute.
Yes. So basically, we're gonna create a stage. So stage basically tells us how many minutes we're simulating for now. Like in reality, you're gonna have like a while loop, while true or something like that, and you're gonna break inside it whenever something happens. For example, you can have a try except or something like that. But for our purpose, it's gonna run every minute for a stage amount of times, basically. Yeah, in this simulation. Yeah. Yes. So the step function is very simple actually. So again, why do we need a step function? Because every time it runs, see, it runs stage amount of times basically, right? So each time it runs, it calls this step function. So the step function is basically going to represent here all the logic that we're going to run every time we're sampling in this case, like every time the gauge runs. Okay? So the step function, you can think of it as the brain of our gauge, right? So here we can see that the brain is not that big. We just have two lines of code. So the first one, what it's going to do, it's basically going to call the ability one, which remember it was read sensor. So meaning we're gonna basically think of it like this. The gauge is just reading the like the discharge, let's say, at this moment, basically. Now it's gonna store the value that it has read, okay, and it's gonna try to transmit it, basically send it to the cloud. That's it. So this is basically the whole brain of this streamer. It reads the value, tries to send it to the cloud. Yeah. Any other questions? So even if the step was defined inside the parent class, it would not change anything, right? Very good question. So why do we do this, basically? Why we use inheritance and why do we try to make classes and so on? Because this gauge class is going to have a lot of functionalities that any gauge is going to have. All gauges need to read, all gauges need to transmit, all gauges should have like some form of stack or queue or whatever of messages that it's supposed to send to the cloud. All gauges should have some form of alarm, and of course they should be able to report to a human operator or whoever reads these gauges basically. Okay, so this is basically it's the basic functionality of this class. Now, as you can see, we haven't defined the step function inside the parent class, right? So if you try to instantiate the parent class and just do like, I don't know, let's say we call it gauge parentheses, like we construct a gauge and we say dot run, it's not going to work because the base class doesn't have a function, a definition for the step function. Okay? Now, this is a very important concept in object-oriented programming, and it basically means whenever I make a child class like naive streamer or the next gauge we're going to create, this pattern is called polymorphism. So what polymorphism actually is, I can have the basic functionality in the parent class, but in the children classes, I can have different forms of a specific function, basically. So this different forms will have different brains, basically. This is called polymorphism, and it's a very important application of object-oriented programming. So I didn't use OOP before, and I'm trying to track the stage back to where 1 minute step is defined. Which line? Good question. Let's see, where did I define stage? I think it's, okay, stage series. Where did we define stage series? Uh, Let me see. Okay, this is the class definition. Okay, actually, where's stage coming from? Stage equals. Yeah, I think if it's none, it defaults. Did I define it somewhere? Yeah, we defined it
So you
here.
do like a days equals to. uh, length dot self dot stays divided by 24 by 6, 24 times 60, right? That's
Yeah,
assuming minutes.
yeah, it's from here. So stage equals design dot storm, basically. It's from here.
But like a design storm, does it say every minute? They want to see where exactly does it say every minute.
So design storm creates a panda data series, basically.
Hmm.
Okay, the length of this pandas data series is basically our time points, basically. So the length of the pandas data series is just going to be equal to n. We could have just said n as well. The same. Yes, someone actually, yeah, tracked it down as well. Yes, that's correct. Okay, all right. So now, if there are no more questions, we can go to part three. Okay, so now we're gonna basically try to create a smart gauge. So what the smart gauge is gonna do is gonna do this, okay? So it's gonna use, first of all, adaptive sampling. We're not gonna sample every 1 minute, basically, unless we are in event mode, okay? So if it's in quiet waters, like nothing is happening, like for example, let's say on our hydrograph, we're around here, basically, on this part of the graph. We're just going to sample every 15 minutes. So see, we already cut the sampling rate into 15. Okay. Now, when it's in event mode, basically, it's going to sample each 1 minute. Okay, now we're going to have some detection rules. Basically, we're going to have rapid rise, meaning like the stage is going to keep climbing. If it climbs more than 1.5 feet per hour, then we enter event mode and we sound the alarm. Something is wrong, basically. It seems a storm or something's on the rise, right? And we're going to have a flood stage, basically means the stage at which we can declare that there's a flood. This can depend on the architecture, whatever, the bridge sizes, like how shallow the water is, and so on. So it can depend. It can depend on the like local hydrography or whatever. Okay, so let's see how we actually do this. Okay, so what we just said, it's we can encode them as constants. So these are the tunable knobs. Okay, so they're pulled to the top. We usually define important constants at the top. So basically, the fellows can experiment as well. Like you guys can experiment. You can change any kind of these constants and see how it changes the gauge. Okay, again, we're going to create a child class, basically smart gauge. And now this is very interesting. So we're gonna have a different constructor, a different initialization. And the problem is whenever you want to create like a special constructor in a child class, you first have to call the constructor in the parent class. Okay, so super.init, this one basically what it does, so it calls the constructor of the gauge class. Okay, but then for this smart gauge, we basically need much more information than we were storing in the parent class, right? So now we need a history. We need the hourly samples. We need to have a Boolean variable, which basically Boolean means true or false. We should have a flood alarm and some other not so important things, basically. Okay, so these are attributes that are on top of the gauge class. So you can think of the gauge class as a base class, and you can think of these attributes. So these attributes are gonna only appear in a smart gauge, but not in a gauge class, in a normal gauge, basically. And what's interesting, we can have a hierarchy. Like, for example, we can instantiate a smart gauge that has a different brain than this one. Okay? We're going to create this rise per hour function, which basically what it does, it appends the new reading. It basically drops anything older than an hour, and it returns the current stage minus the oldest kept stage. So it basically returns the increment. Okay. and the units are in feet per hour. Okay, now we're gonna define the actual brain of our smart gauge. Okay, so always we start with the backfill. So let's say, can you suppress or override some attributes from the parent class if needed? Yes. So usually, if you want to suppress, you just don't use them, basically. But if you want to override, that's very easy. You can just, like, for example, I could have done here, after the initialization of the parent class, I could have just changed, I don't know, let's say, whatever, used mAh to like 500. So let's say we already used 500 milliampere hours or something. Yeah. Okay. Yeah, so first we flush buffer. Why we do this is, for example, let's think of it in terms of streaming, right? So let's say there was an outage, right? And it was running throughout the outage, but now the link is back up, right? So we can send data to the cloud. Then the first thing we want to do, we don't want this backfill to accumulate, right? So the first thing we're going to do, we're just going to flush the buffer and send all the data to the cloud. Okay, then the next part is basically going to be the adaptive sampling, and it's going to be done every 15 minutes. So quiet this will be 15 basically. Okay, so it only does it every 15 minutes. So we already encoded something very important, sending information to the cloud after outages and the adaptive sampling. And again, similar to the naive streamer above, we're gonna get sensor reading, okay, and we're gonna append it, and we're also gonna calculate how much is the rise, basically. Okay. Now let's look at the detection rules, basically. So the detection rules, rule one is gonna be the rate trigger, right? So if we are calm and the water is rising more than 1.5 feet per hour, we switch to event mode, basically. We flip the Boolean to true. Okay, we sound the siren locally and we send one alert. Okay, this fires before the flood stage, which is important because it can give us early warning that usually buys the town time. Like I think even in tornado warnings, they do similar stuff basically. Also, for there's more movement possible than in floods as well. Or okay, so now rule two. Okay, rule two is basically the thresholding logic. So the first time the stage reaches 10 feet, we sound the big alarm. Okay, so this actually should alarm everyone. Okay, now. We leave the event mode only when the water is back below 8 feet and it's falling. So basically, after the storm or the flood went away, basically. Okay, and now the data diet. So basically, once an hour, we send a summary. Basically, yeah, and we can usually make it like we can call the record function to make it human readable. Otherwise, we send a different message every 30 minutes, basically. And now, what's the interesting part? Remember, we had 1,440 messages for the naive streamer. The smart gauge, which is going to send 25 messages, basically. And this is going to increase when there's floods. So this is 1.5 kilobytes instead of 84 kilobytes, which is very important. Now, let's run this and see the report. Okay, so the naive streamer, again, is going to send 1,440. This one's going to send 25. And because of this, instead of working for just 2 months, we're going to have it working for 8 years, which is amazing. This is a huge improvement in gauge design. Okay. All right. Um, let's also run this code, see what it does. Okay. See, so we have the local alarm fired at 7:15. Let's see, when is that? Uh, Around here, basically. So it fired at the right time. And let's see how much later did we get to the flood. So around 3 hours later. So basically this will buy us around 3.3 hours to prepare for the flood, which is pretty useful, basically. Tomorrow we'll try to do even better, even more hours. Okay. But tomorrow we'll assume we have a lot of gauges, not just one. Okay, now, are there any questions so far? Okay, if there are no questions, let's go to part four. Oh, there's a question. Yes, I can send them to you, but I can also send you the link. Uh, so you can just pull this GitHub. Let me know if you got them, basically. Okay, so part four, the storm test. So basically, can we make the sensor talk to each other? Okay, got it. Thank you. Okay. Can we make the sensor talk to each other so rain gauge upstreams informs the gauge downstream? High frequency sampling, is this a smart way to structure? Yes, that is exactly what we're going to do tomorrow. We're going to have the gauges talk to each other and talk to the cloud as well. We're going to have a hybrid system tomorrow, which is going to have both edge intelligence and cloud intelligence. And yes, as you will see, that one is going to buy us a lot of time and is going to allow us to see the storm in much more detail. Okay, so all right, so now the storm test. So usually when the storm is very strong, what do you think happens to radio waves? They get distorted, and usually the signal doesn't reach. So these 3 hours actually can buy us a lot because at this time when we're in the flood stage, the sensor might not even react anymore, basically. All right. So now let's schedule the outage. Okay, so we're gonna call the crossing time. The crossing time is the time when we went above 10 feet. So when the flood started, right? So we're gonna do it basically 1 hour after the rise begins. Um, for some of the formulas, yes, but the actual code, I wrote it. Right. So, okay, so we're gonna build the outage window, which is gonna be around 12 hours. Okay, and net is gonna be per minute true and false. Basically, is gonna tell us is the network up or is it down? Basically, um, right. Okay, so we're gonna have a naive streamer basically on the system, and we're gonna have a smart streamer. So we're gonna compare them side by side, basically. Okay. Uh, Yeah. So now let's define the cloud flood news, basically. So when did the cloud first learn about the flood? This is the important part for us, basically. We're gonna scan everything the cloud received for any reading, like both the smart and the naive gauge, and take the earliest arrival. And if none arrived, we're just gonna say none. If no arrival was found, basically. And the arrival time is what counts because backfilled reading is not very useful. It's useful only when it arrives, actually. Okay. Now, the first local alarm is just basically going to tell us when the first siren actually uh, uh, fired, basically. Okay. Let's run the loop. Okay. So again, the outage was around 12 hours. Look at this. The naive never made it. It never made it. But because the smart one was able uh, to fire the siren early, even when the network was down, it returned the backfill and it buffered every reading basically. So the cloud record was gap free. Yeah, this is very important, and it showcases smart gauge design. Okay. Now here let's plot it as well. See? So this is again the same it's the same storm, but it's when the smart gauge alarms fired basically. So it fired basically close to the outage, which it's not that good still because in reality we still wouldn't have made it basically. But if we have a tomorrow we're going to have a system of gauges, and if that's the case, we can uh, uh, we can have it much earlier than just one basically. Okay, finally let's have a scoreboard. Okay, so the final scoreboard is basically this. We're sending far less messages. We're draining the battery far less. The battery life is much better. Uh, the flood was already warned locally. So, for example, let's say we have an alarm, right? In let's say in the region, we were actually firing a real alarm that could, like alert the citizen or whoever lives there, basically, to uh, to get out of the area, basically. Yeah. So this basically showcases the importance of the gauge design, basically, and this is the core of edge computing. Right. So to wrap up, basically today we learned about edge computing. We designed different gauges. We saw how gauge like edge computing intelligence can actually offload some of the tasks of clouds to the network of edge devices, and we showed the real importance of edge intelligence. Any questions?
Yeah, so we have about 2 minutes of time, and Mihail and I are happy to take any questions that you have. So if anybody doesn't have access, I think you should have access to this, access to the Jetstream 2 folder that we have here. If not, all these notebooks are also on our GitHub page. Yeah, I think they should be able to load this on like Google Colab, right? And run. Yeah.
Yeah.
Okay. So the biggest takeaway is that, by having some few extra lines of codes, right, on small program on the edge device, right? And so we were able to send the message, the edge device was able to send the message to the cloud a few hours later, right? When the network became on as well. But critically, it was also able to because it had a backup channel, even the primary channel failed, it was still able to alert the local system, right? So this is like a clear advantage over a naive system which does nothing but collect data and send it to cloud. Okay, if there are no questions, then we will see you back tomorrow. Tomorrow we'll talk about the hybrid systems, right? What are their advantages? And then again in the afternoon, we'll do a hands-on. Uh,
There is actually a question. So smart sensor, great from industry perspective and applications, but from scientific point of view, consistent and stable data generation is still valuable. That is correct. But the purpose of our system was to create a flood early detection system, basically. If your purpose is to model how rivers actually flow and how they work, then yeah, you can just have continuous data collection at any sampling interval, maybe even millisecond or nanosecond, if that's important for you.
okay, so the next question is where can we have the PowerPoint? Is the PowerPoint on the GitHub?
I don't think so.
Okay, but we can upload, right?
Yeah.
Okay.
Are DL models deployed on the cloud for operation to predict the stage? For example, when there's a gap, are you aware of any agencies that are doing that? So probably DL deep learning, I think. Stage forecast.
Probably, right? So most of these forecasting models, right, nowadays are they probably have some deep learning component there. Are there any agencies doing that? That I'm not sure. Maybe this is a better question for our
The
hydro science
hydrologist.
faculties like Vidya and Ibrahim. Okay, all right. I guess we'll see you guys tomorrow. Take care and thank you very much for attending. Right, so this was a very interactive session. Thanks for all the questions and see you again tomorrow.
Bye, guys.